Good evening, everyone. Am I audible?
Yes, ma'am.
Yeah, so let's wait for a couple of minutes. I guess not everyone has joined. We will start in a few minutes. Can you see my screen?
Yes, ma'am.
Yeah, so let's start with a brief of what we had done in the previous class and what methods we have discussed so far. Can you recall those?
By using the adsorption phenomena, how to remove the suspended matter present in our water. So, various
Yes.
type of membranous absorption,
I'm asking about like not the current week, prior to that, prior to adsorption, what methods have we discussed? Yeah, you should like it's better to recall every time what we have done so that it's easier for you all. Can you recall that? So far, we have learned coagulation, flocculation, sedimentation, filtration, yeah, equalization as well. Yes. Uh, yes, and I'm not forgetting anything. Now, we will be looking into adsorption process from this point. Yeah, so let's start with what is adsorption. So, adsorption is a process, is it's a sort of physico-chemical process where, you know, let's say this is the solid surface, and we have a closed chamber, like it can be anything. And here we have liquid filled, or we might have some gas also. So the liquid molecules or gaseous molecules, they interact with the solid surface and they form a bond. It can be any bond, chemical bond or physical bond, and they stick here, they sit on the surface due to some force of attraction, right? So here the molecules that sit on this surface of solid, these molecules are nothing but adsorbate, right? And the solid surface is known as adsorbent. And the entire process involving the interaction of adsorbate and adsorbent is nothing but known as adsorption, correct? So now we may have multiple adsorbents available and we may apply it for various applications, right? For example, one of the practical examples that we use uh, in our daily life is let's say you have silica gel. So this silica gel has tendency to absorb water molecules, right? So it has high affinity for water, right? So it won't allow moisture in any uh, material. So if you buy a new water bottle, so to avoid moisture and further growth of microorganisms, silica gel is added, like a packet of silica gel you will be uh, seeing in it, right? Next is you in your household filters, you would have seen if you like if any one of you have opened it sometime, then you would have seen a carbon block, right? I can show you the picture how it looks. Mm, like this. Yeah. See, from outside you won't be able to understand, but this is nothing but carbons or you know, carbon block. Like so, it will be shelled inside. You will have uh, one support or storage of it, and this is how it would look. Yeah, so this is in the form of granules. These granules are, you know, they are compressed to form a block, right? So by compressing, we prepare a block of this sort, which is packed inside a filter unit or inside a unit where you pass water through this block, and it will have some pores through which water will pass, and any impurity which we want to remove, it will get removed. So basically, activated carbon is one of the well-known and most popular, um, you know, adsorbent used so far.
Absorb.
Yeah.
Yes, ma'am.
Okay. So there are multiple adsorbents which are further used. Um, yeah. So this was one example. It can be used for some different applications as well. For example, if I give you example, apart from water treatment, let's say you would be hearing that CO2 emissions has been increasing day by day, and you want to reduce the carbon footprint in the atmosphere, right? So you want to reduce basically the amount of carbon dioxide emitted from industry or the amount of carbon dioxide in the atmosphere. Can you mute yourself? There's a disturbance. Yeah, thank you. So, how can you do that? Uh, One way is obviously planting trees, right? Because it uses up carbon dioxide and releases oxygen. Next, another method, if you are uh, thinking of industrial perspective, then what you can have is if you let's say have a mixture of CO2 and N2, which is obtained when you burn coal in power plants to generate electricity. So this CO2 will be absorbed on, let's say you can use an adsorbent here also for this process. So similar, you can have like basically you are separating one component from another component by having more affinity towards one component out of the mixture, right? So in case of wastewater, you will have pollutants plus water, right? So that's how it's wastewater. So basically you want to separate pollutants and from water, and you allow pollutants to sit on the adsorbent. Now if we talk about wastewater matrix, then it might have n number of pollutants, right, in it. So in that case, it's possible to have specific adsorbents as well. For example, if I tell you, then there can be some dyes present which are not degradable by microorganisms. So you cannot use activated sludge process, right? Then you can have heavy metals, right? Then you can have water in your wastewater. So there could be multiple pollutants which might not be removed by conventional methods. So in that case, you can use this adsorption process. But here the pollutant might have different characteristics, and for example, Dyes, they are organics, right? While heavy metals are nothing but ionic species, for example, Pb2 plus, Pb2 plus, right? So all these have different characteristics and might have different interaction with the adsorbent. So in that case, you will have uh, a choice of adsorbent. In that case, there are various adsorbents available, and you need to have some laboratory tests to check which adsorbent is specific towards which pollutants or which type of pollutants you can uh, rather say. So, as I mentioned that one of the common adsorbent available is activated carbon, right? Then you would have heard of nanotechnology, right? So can you define what is nanotechnology or nanoparticles?
The particle have the size 10 to the power minus 9 meter is called the nanoparticles.
Yeah, so 1 to 100 nanometer, if any material has having size, at least one of the dimensions, right? So that is nothing but nanomaterial. And what is the advantage of using nanomaterials here or anything in nanoscale?
Small size means larger volume, large surface area. So for the absorption, the surface area is large means absorption is also large.
Yeah, very right. So let me show you one image to um, so that you will actually be able to relate. Yeah, you are right. So let's say this is bulk, which means it has microns or maybe some millimeter, centimeter size. So as you keep on decreasing the size, what happens? The exposure, like let's say only this much area is exposed, while so inner area you are not able to expose, right, to the outer things or its exterior. Now, when you keep on decreasing the size, inner area is also being exposed to the exterior or the external medium, right? In that case, you are actually increasing the surface area, right? And higher the surface area, it means that more exposure of the nanoparticles you will have with the uh, matrix in which it is present, right? So let's say here our matrix is wastewater. So if I'm using nanoparticles, um, right, as my adsorbent, so it will have high surface area, and which means that it will enhance the efficiency because it will have more of its area exposed to water and hence more uh, active sites. Like how does an adsorbent work? So adsorbent basically has you know let's say this is a solid surface and this is an active site. So this active site could be a positive charge on the adsorbent surface or some negative charge on the surface, or it could be some functional group like OH, COOH, or CHO, any functional group, right? Which can have affinity um, to other uh, species. For example, let's say your adsorbent has negative surface charge, like it is having negative charge. So what will it do? It can have affinity towards any species which has, let's say, X plus charge, right? So that is sort of electrostatic force of attraction because negative charge will attract the positive charge. So you sort of select, depending on the pollutant you want to remove, you sort of select the adsorbent characteristics, right? Now, let's say these are the active sites which are responsible for adsorption. So when I convert the bulk material to nanoscale, it will have more active sites. So these sites are nothing but active sites exposed, resulting in higher removal efficiency of pollutants, right? So that is why we can have any material which we can try to convert it into nanoscale by either crushing it or some different synthesis methodology. And if not nanoparticles alone, we can have even the composites of two nanomaterials so as to enhance the efficiency, to enhance the affinity towards the pollutants, or uh, any different requirement which we might have, right? Uh, then, if we talk about adsorbents, then as we mentioned that they usually have different properties, and they could be they could be of different size, shape, and different properties, which like and also the size, shape, they define the surface area, hence their efficiency. And further, depending on their chemical structure, it can have uh, varying thermal resistance, chemical resistance, right? Also, their structure might have different porous structure, right? So pore diameter also plays an important role, and their hydrophilicity, hydrophobicity. So all sorts of parameters you need to take care, and they affect the efficiency of adsorbent. So while you are choosing any adsorbent, first is you need to look into what uh, pollutant you want to remove. Based on that, you need to check the literature whether like what sort of uh, affinity can be exploited so that you will have maximum removal, and depending on that you can tune uh, your adsorbent characteristics, right? And later you can have a number of adsorbents, and the one which is having highest removal efficiency, uh, right? So that will be selected for the particular application. Now, for any adsorbent, uh, the criteria to select, or an important criteria for parameter for adsorbent is adsorption capacity, right? So adsorption capacity is nothing but how much of unit weight, how much amount of pollutant can be removed through adsorption for unit weight of adsorbent, right? So usually you measure it in terms of milligrams of pollutant absorbed per unit gram of adsorbent, right? So this is nothing but the amount of pollutant removed uh, per unit adsorbent, right? So that is nothing but adsorption capacity. So higher the amount of adsorption capacity, more is the affinity towards the pollutant, and more is the specificity, and you can choose the one which is having higher absorption capacity, right? So is it clear so far? Yes.
Yes, ma'am.
Okay. Uh-huh. So let's move forward. Okay, so next is if we look into the process, uh, absorption process as whole. So, what is the mechanism for absorption, right? So, let's look into that. So, if we uh, like the definition says that let's say you have a beaker, uh, you have water with dye present on it in it, and this is the adsorbent material which you have added. So, from your eyes, what you will see, let's say this adsorbent is very specific uh, for the particular dye. So it immediately absorbs the dye, right? So what you will see through your eyes initially, it will have some color. Let's say it was having pink color. So pink color will either reduce or it will disappear, right? So this is what you will see from your eyes, but that is not uh, if you look at molecular scale, and this is involving multiple number of steps, right? So first is dye molecule is present in the water solution, right? So water as a whole solution or dye molecules, they are present in the bulk. Now this interaction is involving two phases. One is liquid phase, another is solid phase. And when you are involving two phases, you will have boundary layer, right? One is this is the boundary layer, boundary or the separation between solid and the liquid, and there will be a bound film, liquid film, and the solid film, let's say, where you will face some sort of resistance for the transport of material, right? So there are number of steps involved. Based on this number of steps involved are first is let's say this will be the bulk, right? So from the bulk, it will go to the exterior film which is surrounding the particle. Now, if you say that there are two films, then liquid film and the solid film, it has to uh, uh, overcome the resistance, and depending on the characteristics, you might have more less liquid resistance and more solid resistance and vice versa. So first step is the transport from the bulk of the solution to the exterior film, and this is nothing but the film surrounding the particle, right? So this resistance it has to overcome. Now next is once it has reached on like near the surface, then there are some exterior sides. Okay, now let's say it has reached the solid surface, but this solid surface is, let's say, spherical, and this is the external surface, and after that it has some pores also, right? So these are nothing but pores, and pores might have any random shape, right? So firstly, it will adsorb onto the external active sites which are present, right? So active sites could be here also on the surface, and it could be inside the pores as well. So firstly, since for the adsorption inside the pores, it has to travel more, it will adsorb immediately on the surface itself because it has nothing to do but absorb, right? So, uh, whatever might be the possibility, it will absorb here. Then there are chances that the active sites are inside also inside the pores. So it has to first travel inside the pores. So next step will be the migration inside the pores. And lastly, adsorption onto the internal surface sites, which are nothing but the active sites inside the pores, right? So these are nothing but the steps involved for absorption and the uh, mechanism for it. So now, yes, I have been saying that there adsorption is nothing but interaction of solute uh, or adsorbate with the adsorbent, and there is a sort of force of interaction which uh, allows the adsorption process to occur, right? And that forces of attraction could be divided into two. This is uh, the first one. This is the second one, right? So first is physical force or physical adsorption, or you can even say physisorption. It has multiple names, right? And when you have physical adsorption taking place, you will have only physical force of attraction prevailing. In that case, what could be the physical force? It could be van der Waals force of attraction, even hydrogen bonding. You can say it comes under physical adsorption, right? So if the adsorption takes place through van der Waals force of attraction or hydrogen bonding, it will be classified as physical adsorption. Now, physical adsorption is not so specific, right? Because between any two molecules, you will have physical force of attraction, and it's very weak, but you can say uh, it can exist between any two uh, molecules, right? So this adsorption can exist between any adsorbent, but you can say the efficiency will not be up to the mark because it's not so specific, and hence it will remove, but to a lesser extent. So how will you uh, let's say this is the solid surface, and solute will sit on, like it will start sitting on the solid surface. Let's say the entire solid surface is covered, but the adsorption here is taking place through some weak force of attraction, which is van der Waals force, and you still have more of solute in the medium. Sorry. Yeah, so in that case, you can have even the force of attraction between these two molecules as well, right? Van der Waals force can exist between any two molecules, right? So even this too will have a van der Waals force of attraction. So again, it will start like molecules will start setting and form a next layer, and hence you can say this option is can form multiple layers of adsorbate on the adsorbent surface, right? And it's sort of a multi-layer adsorption. Is it clear?
Yes, ma'am.
Okay. Yeah. So next is another type of adsorption process, which is chemical adsorption. And chemical adsorption is nothing but, as the name suggests, it involves some chemical bonding, and even it is known as chemisorption, right? So this is the another name. And here some strong chemical bonding or chemical force of attraction exists between the adsorbent and adsorbate. And say you have a um, COOH group, right? And you would have heard of ligand bond formation, right? So COOH or even OH. These are nothing but oxygen. These are high electron rich, you know, functional groups because of the oxygen molecules, right? Or even NH2. These have a lone pair of electrons, right? So if these are able to share their electrons, and that is nothing but some chemical bond, right? So let's say it has the ability to form ligand bond, or another name is coordinate covalent bond. So this bond is much stronger as compared to the physical absorption or physical force. Now, let's say the pollutant is represented as M, and it is attracted towards the lone pair of electron, and let's say it has that d orbital which can accommodate this lone pair of electron, and the nitrogen can share, right? So this will go to this lone pair, and it will be now shared by both, right? The lone pair. So the number, the amount of M which will go on this surface, it will depend on the amount of NH2 present, or the amount of lone pair, which could be because of any functional group OH, COH, or NH2. It will depend on the functional groups, right? So it will be only on the surface or inside the pores, right? So once all of these are consumed, uh, the adsorption will stop. So you can say that it will form only one layer of adsorption, right? Because once the adsorbate has sit on this functional group, this is occupied, right? Now, this force cannot exist between another molecule. So it's very strong force which is prevailing and which is attracting the adsorbate. And once all these functional groups are occupied, the adsorption will stop, right? So it's sort of very specific adsorption process, and also only monolayer will form because the functional groups only on the surface, and only these will be able to remove the pollutant. So you can say it's sort of irreversible, specific, and monolayer adsorption taking place to chemical adsorption. So for pollutants to have, for good removal efficiency in wastewater treatment, you should prefer the adsorbents which are, you know, uh, having chemical adsorption taking place, right? So is it clear so far?
Yes.
Okay. So the next thing that we should look into for the absorption is what factors does the absorption uh, process is affected by. So yeah, obviously it depends on what type of adsorbent you have taken, nature of the process, and the parameters. For example, the water characteristics, right? For example, if uh, what is the pH of water, what is the matrix of water, for example. If you want to remove one pollutant, but uh, there are chances that it's not just one pollutant, it can be n number of pollutants, but you want to specifically target only one pollutant. So yeah, so the water matrix also affects then how much amount of time you are providing, the temperature, right? So there are a number of factors, and let's look into them one by one. So let's start with first one, which is the pH of solution. Now, as I mentioned that there could be number of possibilities of bond formation for, let's say, we are specifically looking into chemisorption, right, which is mostly used. So for chemisorption, let's say you can have electrostatic force of attraction. Then you can have coordinate covalent bond, right? Uh, these two are major bond formations for chemisorption. Now, in the case of adsorbent, uh, let's say you have you want to remove any heavy metal which is having Mn plus charge, right? So it is a cation, right, existing in water matrix, and your adsorbent is having these active sites. Now, surface charge also depends on the pH of solution. And how does it affect? Let's say you have pH, like pH is very acidic, right? So it will have more of H plus. So these H plus will also have the tendency to sit on the adsorbent, and there will be a saturation. So more the H plus, more will be the positive charge of this adsorbent. Now, as you keep on increasing the pH, the amount of positive charge will reduce, and there will be a certain pH where the adsorbent will be converted into totally negative charged, right? So there will be a transition from positive charge to negative charge, and this we have also looked into, uh, right? Where like the point of zero charge, right? So this is where it applies. So point of zero charge is the charge where the adsorbent will have neutral charge or the zero charge. So below that pH, it will be positive, and above that pH, it will be negative. Right? So that is the concept of point of zero charge. This we have looked into detail in the previous classes as well. So now let's say you want to remove a pollutant with Mn plus charge. So in that case, since this is a cation, and for electrostatic force to prevail, you need your adsorbent to have negative charge, right? So as the negative charge increases, your efficiency will increase, right? So that is how the pH of solution, it affects the removal process. And yeah, so depending on the amount of pH your wastewater has, the efficiency will be determined. So in the case if your parameters are not according to your uh, requirement, you can actually add some of the chemicals to enhance the efficiency as well, right? Next factor is the contact time. So, uh, yeah, what happens actually is, let's say you have this adsorbent with active sites, right? So, and there are number of Mn plus molecules, and which needs to be removed. Initially, you can see all the active sites are vacant, right? So these vacant sites, since they are more and more, like the rate of absorption will be more, because the rate is dependent on the amount of active sites, right? And it can be also dependent on the adsorbent adsorbate concentration, right? So we will look into the kinetic models as well, but yeah, basically it should depend on both, right? So more the active sites, more will be the amount of molecules removed. So initially, if you see, more and more active sites are vacant, and there will be a drastic and faster absorption taking place. Uh, while as the time proceeds, let's say this active site is occupied. Now, uh, the molecule does not know whether it is occupied or not, and it will try to interact with all the active sites. So the rate will reduce because it will have to search for the vacant active sites, right? So Now, as the vacant sites reduce, the rate of adsorption reduces, and there will be a time where all the active sites will be consumed. So initially, you can say it is it is very rapid adsorption, which gradually slows down and equilibrium is attained, right? So you will see the uh, concentration of pollutant in the, let's say, bulk. It will, let's say this is the concentration at T equals to 0, and as the time proceeds, the concentration will reduce. So initially it will be very steep, and later it will slow down, and it will attain equilibrium, right? So this is the scenario of concentration in the water matrix. Now, if you look into the scenario in on the surface of adsorbent, so it will be reverse to it. So it will steeply increase. This process will slow down, and it will attain saturation because now all the vacant sites are occupied, right? So this is the amount, or you can say the adsorbent, the adsorption capacity QT with respect to time, or you can say this is the concentration in the water with respect to time. So this is how it will look, right? But the nature or the steepness will be same, but the trend will be opposite for both. Like in the water, since it is consuming, so it will go down, and since the adsorbent is having more and more with time, it will rise, and then equilibrium will be achieved. Yeah. So this is how the contact time uh, affects. Now, in industries, what you do, you use the adsorbent not in like in a fixed bed column, right? So it will you will have a bed of adsorbent. So the efficiency of this process will depend on the amount of contact time you are providing, right? So more the amount of contact time you provide, more will be the efficiency of the process, right? Next is the initial concentration of adsorbate. And as we have discussed, the rate of adsorption depends on both the amount of pollutant and the amount of adsorbent, right? So more the amount of pollutant or the adsorbate, more will be the rate of the process, right? Uh, yeah, here so far. Yeah, just give me a moment. I will be back in a minute. Yeah, let's start again. Uh, yeah, next is the temperature of the process, and absorption is usually exothermic in nature, and depending on the temperature, it can like you would be knowing Lee Chatterjell's principle as well. So Yeah, so depend, and since the process is equilibrium based process, so it can also define uh, the efficiency, right? So yeah, now let's look into the absorption kinetic models as models. So these models are very general and they have some basic assumptions behind them as well. So for example, first order kinetics or second order model, right? So here, let's say first order kinetic model, it assumes that uh, the absorption process, it completely depends on the amount, it's sort of physical absorption, and hence like physical attraction happens, and hence it is reversible, right? So uh, and also the rate is proportional only either to you know uh, the amount of, like, only one parameter, only I guess on the adsorbate or on the adsorbent, right? So this will depend on the amount concentration of adsorbate and the concentration of adsorbent. So here you can say one is pseudo because um, one is so high. For example, let's say you want to remove uh, organics which is contributing to a COD concentration of 2000 milligrams per liter, and as compared to that you are using only 100 grams of adsorbent, let's say. So this is not enough for removing the entire COD concentration. So you say that COD here, uh, you know, is the limiting factor. So there will be one limiting factor when you uh, talk about first order kinetics. Next is second order model, where you say the rate is proportional to both adsorbate and the adsorbent. And here again you see it is assumed that uh, chemical adsorption takes place, right? And hence it is irreversible in nature. Further, there are models which you can use to check whether the intraparticular diffusion model, intraparticular diffusion. So, whether the diffusion inside the pore is the limiting factor or not. For example, we have seen here that there are n number or like let's say 4 to 5 steps involved for the adsorption to take place, right? So each of this process has their own rate, right? So to explain you this, let's take an example of a relay race, right? So in a relay race, there will be, let's say, four candidates which are uh, which who will be standing at a particular distance, right? So that whether you will win the race or not will be depending on the slowest person, right? Because as compared to the slowest person, rest of them uh, they will be running very fast, right? So similarly, out of all the rates for the process, the rate determining step will be the slowest step in the process, right? So out of all the process, slowest step will define the process. So here through intraparticular diffusion model, you are looking into whether diffusion into the pores, they are actually it is controlling our overall rate of the process or not, right? So yeah, and similarly, void model, it checks for the surface diffusion role in the adsorption kinetics. So there are multiple models, and these all have some assumptions. So when you try to fit your model into your actual experimental data, you will find out what is the mechanism behind your actual uh, experiment or your process. Yeah, next is adsorption isotherm. So this adsorption isotherm will help you find out the adsorption capacity, right? Which we had described as how much amount of pollutant you can remove by using what amount of per unit adsorbent, right? And again, you are having different assumptions made while you are deriving these absorption isotherms, right? So the one which fits more will be the one which you can say defining your process. So how do you find out actually where like what is the better fit? For example, you have the experimental data. You want to find out which model fits better. So what are the ways of doing it? Can you describe this in brief? Okay, so uh, okay, so let's say you are fitting multiple models in data, and you want to check whether the fit is proper or not. So for that, there is a method in statistics which is known as regression, right? So you check, you perform like in computers nowadays already the algorithm is set. So you check for the fitting parameter, which is r square value for a fit, right? So when you use Excel or some other software for fitting the models, basically you will use Excel Origin, right? MATLAB for fitting the parameters, right? So you uh, check for the r square and you compare the r square. So the one, so for a good fit, it should have values greater than 0.95, right? This is a thumb rule. And, uh, you know, the one which will have better R square value, you can say that is a good fit and that fits more to my data. For example, let's say you fitting two models, which is Fundlik and Langmuir. So in case of Langmuir, let's say you are having 0.97 and for uh, this is for Langmuir and for Fundlik, let's say you are having 0.89. So you can say this one is the better fit. Now, if we talk about the isotherms, then again there are various assumptions made, and you can go deeper into it. And uh, here again, one uh, assumes, for example, Frontic model assumes that like which is more realistic, but Frontlik assumes that the adsorption is heterogeneous and multi-layer adsorption takes place. And again, it assumes that not all the active sites are uniform, right? But on the other side, Langmuir adsorption assumes that more or more more or less all the active sites they are uniform, and you have uniform active sites coverage, and monolayer or chemisorption takes place, right? So depending on your assumptions made, you can choose the it's like which mechanism is taking place. But ideally, not single adsorption isotherm fits, right? So these are the basic or the extremes, right? So, which is not the case in the real scenario. So, you might have the combination of assumptions in um, different more models. There are like Temkin. Redlich and Peterson model. So these all are nothing but the advanced version of isotopes. Next is monolayer and multilayer adsorption, and this we have been uh, like this term we have been using very often uh, since this class, and for now you would have understood what is monolayer and multilayer. So multilayer is usually because of the physical adsorption, and you see um, the pollutant can even adsorb on the pollutant molecules, and this only happens when there is, you know, physical adsorption majorly, right? And let's say you have monolayer, so this is multi-layer, and for monolayer you will have only one layer, and usually for chemisorption. Yeah. Uh, Again, you have BET equation for surface area, where BET again is the isotherm, and isotherm is nothing but a terminology used for any process which is performed at constant temperature, which means iso means a constant, thermo means a temperature, right? So isotherm is nothing but whatever performed at a constant temperature. So BET will help you. So you are finding out by adsorbing a gaseous molecules on, like usually nitrogen, on the adsorbent, and by doing that you will use a equation which is given to you by in the lecture notes, and that equation you can use it to derive the surface area, right? So as we mentioned in the initial of the class, that surface area is the important criteria for deciding the efficiency of the process. So more the surface area, more will be the um, efficiency, you can say, or better it will perform, may it be physical or chemical absorption, right? Because more you are exposing the area. Clear so far? Yes, so clear. We will move to the assignment.
Okay.
Okay. So the first question is, which among the following is not a property of a typical absorbent?
Low surface area.
Yeah, correct. So out of all those, low surface area should not be the one. It should have high surface area, and otherwise it should have high capacity, high thermal resistance, high physical wear and tear resistance, right? So, yeah, correct answer here is low surface area. The transport of adsorbate from the bulk of solution to the exterior film surrounding the adsorbent particle is known as dash.
Film diffusion.
Uh, no, you are mentioning from the bulk of solution to the exterior of film. So there are two diffusions, bulk diffusion and film diffusion. So in to the like let's say this is the bulk and this is the film. So inside the film diffusion is like this is interior internal film, and whatever the outside is there, it is bulk diffusion. So this is nothing but bulk diffusion, not the film diffusion. So from the bulk to the exterior film, right? So this is the key word here. So bulk diffusion is the correct answer. Am I like, are you getting this?
Yes, ma'am. If it is given in interior means that is a film diffusion.
Yeah,
Yes,
yeah.
clear. Yeah,
Okay.
okay. Thank you.
Next is the enthalpy of adsorption varies between dash during physical adsorption. So physical adsorption
20
is,
to 40 kilojoule per mole. Very
yeah,
low.
correct. So it usually involves very low adsorption energies, right? So it is 20 to 40. Next is, what is the size range of micropores as per IUPAC classification?
Diameter less than 20 Armstrong.
Yeah, correct. So can you describe more like what is the pore size range, like three categories of pore sizes? One is micropores. What are other two?
Mesopause
Yeah,
and
correct.
then megapause.
No, it's macropores,
Ah, okay. Macropause. Sorry.
right? Okay. So this is the biggest, this is the intermediate, and yeah, this is the smallest. You can actually look more for the size range and you can remember that for your exam.
Diameter less than 500 Armstrong for mesopause. If the diameter is greater than 500 Armstrong means that is called the macropause.
Okay, let's move next. What is the initial sorption rate? H equals to Ks unit here. QE square. Okay, so for any rate, right, the unit will be concentration per unit time, right? So this would be the thumb rule you can remember, or you can apply it for any rate, right? Or it can be initial, or it can be after some time. So concentration here, you are since you are talking about adsorption, so adsorption will be on the adsorbent, which will be in terms of milligrams per gram of adsorbent. So that is the concentration of adsorbate on the adsorbent, right? So milligrams per gram concentration per unit time minutes, right? So unit here will be milligrams per gram minute. Um, could you understand? Uh,
Yes, ma'am.
yeah. Uh, Next question is, which among the following is not a factor that affects the adsorption process?
Color of the solution.
Yeah, true. Uh, Apart from that, nature of adsorbent, pH, contact time, they all affect, right? So color does not affect. Next is adsorption processes are generally dash in nature.
Exothermic in nature.
Yeah. And what does that mean? What is exothermic?
Heat is liberated.
Yeah, correct. So correct answer is exothermic. The BET theory was developed by this scientist in the year dash. So it's 1938. I am not sure if you will get these type of questions where you will have to remember so much during the exam, but yeah. Which among the following is the correct expression for pseudo first order kinetic model?
Qt is equal to QE 1 minus exponential minus KF into T. Pseudo first order kinetic.
Yeah, so you can say that since it is first order, uh, it will be
So it,
proportional to the uh, minus kt power 1, right? So that, I guess, would be the shortcut for you to remember. right? And the last question is, what is the unit for pseudo second order rate constant? So you need to derive for rate constant unit. So if you want to derive any unit, there are two thumb rules. One is the unit on LHS is equals to RHS, and if two quantities are added, then they both will have same unit, right? So these two rules you can apply for here. If you want to apply, you can say K is the rate constant, right? So this will be Ks. Sorry, K is the rate constant. So you can use any of the two rules here. Both will apply. So simplest one will be one will have or since one is unitless because it's just a number, you can say Ks QE into T will be unitless, right? So for Ks, uh, the unit will be the reciprocal of time into QE unit, right? So for units, if you put up, time has the unit of minute, right? And QE is nothing but the adsorption capacity at equilibrium, which will have unit of milligrams per gram, right? So if you solve this, it will be gram per milligram minute. So the unit of Ks will be gram per milligram minute. Yeah. Are you able to do this? Yes. Okay, so I hope it's clear. So I will be around for 10-15 minutes more. If you have more doubts, um, you can come forward for more doubts if you have. I will be back in a minute or two. So, if you have more doubts, you can come forward. I will be around for 5 to 10 minutes.